When we talk about the dispersion of a dataset, we mean how the data values are distributed or deviate from a central reference point. A larger spread indicates that the data points are more scattered from the central reference point, while a smaller spread means they're clustered more closely around it. In this video, we'll focus on numerical data and explore various measures of its dispersion. Measures of dispersion generally fall into two categories, absolute and relative. The choice between them depends on their purpose in data comparison and whether they retain the original units of measurement. Absolute measures are perfect for understanding the spread or variability within a single dataset, which give you the values in the data's original units. Relative measures, on the other hand, are specifically designed for comparing the variability between two or more datasets that might have different units, scales, or means, as they express dispersion as a unitless ratio or percentage. These are common examples of absolute and relative measures of dispersion. Let's start with absolute measures of dispersion. Let's say we're looking at daily temperatures for a week. If we subtract the lowest temperature from the highest, we get the range, which gives a quick estimate of the data's total variability. This is effective for small datasets. However, any significantly small or large data value can mislead the interpretation of the overall data variability, since it considers only two extreme values and ignores the intermediate data. Now, using the same dataset, if we calculate the squared difference of each data point from its mean, sum those resultant values, and then divide this sum by n-1, we arrive at the sample variance of the dataset. This variance represents the average squared distance of a data point from its mean. This formula calculates population variance for complete datasets. If we take the square root of the variance, we will get the standard deviation, which represents the average distance of a data point from its mean. Unlike the range, variance and standard deviation account for every data point, but they are also sensitive to outliers. Extreme data values can make the spread look bigger than the typical spread of the majority of the data. These measures assume a symmetrical data distribution, like the normal curve, where the distribution of data values are symmetric around its mean. However, when the distribution is skewed, mean shifts towards the tail, which makes the mean a poor estimate of the central tendency. Therefore, variance and standard deviation around this mean do not reflect the typical spread of the data. The interquartile range, which measures the spread of the middle 50% of a dataset, however, does not assume a symmetrical distribution. This is because it is based on quartiles, which divide the data into 4 equal parts regardless of the data's overall shape or the presence of outliers. When we divide data values into 4 equal parts, the interquartile range is the range between the first and third quartile. Now, to calculate the interquartile range for the temperature data, first sort the data values in ascending order and rank them 1 to n. Then, calculate the first and third quartiles using the following formula. The first quartile is the second observation, that is, 15 degrees Celsius, and the third quartile is the sixth observation, that is, 20 degrees Celsius. Therefore, the interquartile range is 5 degrees Celsius. The quartile deviation, which is also known as the semi-interquartile range, is the half of the interquartile range. It can be interpreted as the typical dispersion of the data points around the median within the middle 50% of the data. Another common absolute measure of dispersion is the mean absolute deviation. It represents the average distance of each data point from a central reference point, which can be the mean, median, or mode. To calculate the mean absolute deviation for our temperature data, we first calculate the average of the data. Next, we take the absolute difference of each data point from this average, sum all these differences, and finally divide by the total number of readings. The mean absolute deviation for this dataset is 2.204. This means, on average, each temperature reading deviates about 2.204 degrees Celsius from the mean. Join me in the next video, where we'll discuss relative measures of dispersion for the numerical data. If you'd like to test your knowledge on this topic, Be sure to check the quiz link in the description below or visit our community page.